Yeah, Min Min already told you about all the things about homework and tutorial and everything, so I don't have to go through that anymore. Min Min was in the course last year, so he knows how things go. So okay, so first of all, what is you have taken courses in probably some of you have taken courses in Millen on math programming. Some people may have taken course in optimization elsewhere in their former schools. Basically, what we are doing now is learning basically to do the optimization when things happen over time. So there's a dynamics involved. And when there's a dynamics involved, how do you optimize in that setting? And this is where the optimal control theory comes in. So we need to kind of have a dynamic system that evolves over time, and we need to figure out how to optimize that system. And so this is basically the main purpose of this course. Uh, I think that, let me see, where is my slide move? Can I do this like this? No, it doesn't work. I don't see a move. Oh, how do you do that?
I think this is a PDF directly, so you just scroll it down. You just scroll
Scrolling
it.
my mouse like this?
Yes.
No,
Yes.
it doesn't work. My mouse doesn't work. Or it works. It works slowly. It has a speed problem. Okay, let me see if it works. No, no, the mouse doesn't work. Now, oh, this is terrible. Okay, this is one. Okay. So as you can see, this is a dynamic system that evolves over time. The time can be both discrete and continuous, but most of the time in control theory, we usually treat the time as continuous because the theory is much more elegant and much more developed. But we do have a discrete time setting in chapter 9, I believe. Uh, yeah, no, now is chapter 8. So discrete time setting in chapter 8 and chapter 9. So we will do that later in the class. As I mentioned to you that we need 1 year of calculus, so you need to know how to differentiate and integrate. And you need a little bit knowledge of what the vectors and matrices are. Not really a big knowledge of linear algebra, but at least you know what the vectors and matrices and there are some operations on those. You need to know something about ordinary differential equations because we will be using a lot of ordinary differential equations. I don't I don't require you to know uh, I don't require you to take a whole course on ordinary differential equations, but I do want you to have some knowledge of those in a calculus course. In a calculus course, if it's a 1 year course, you will have some knowledge of ordinary differential equations. We will see a little bit later what I mean by that. As for the partial differential equation, we will use them later on when we do stochastic control. But again, you will be told what they mean, and most of you probably do not know much about partial differential equations anyway. So we will see how we deal with that later. Primarily, the book goes into the theory of optimal control at a level which is not that rigorous as it will be taught in a math department. It is actually, the book is meant for a business school, and so we will see how much we need, but not what is needed, let's say, in a course in a mathematics department. And we will emphasize on, does my mouse is working for you like this? Can you does that work for you when
Yeah,
I
we can see the pointer.
good?
Yes.
Okay. So we will apply to field in production, which is field in operations management. We will apply to problem in finance. We'll apply to problem in economics, and we'll apply to problem in marketing and some other related topics. So that's kind of what uh, we want to do. So let's see. Isn't there something that says an arrow that allows you
I think
to?
there's an arrow on the top.
Oh, good. That's good. Yeah. Now we are talking. So so we define a dynamic system by a kind of a a state equation, which is actually a differential equation. So what you see, this x dot t, that x dot t is basically another way to say dx dt. Everybody knows what dx dt means. So this is dx dt equal to something. Now notice there's something else coming on, so forget this ut for a while. If I give you dx dt equal to f of xt t, and I give you x0 equal to x0, which is the beginning value of the state variable, we call it a state variable, then what happens? So what does the differential equation do? It begins with x0, and it tells you how the x0 is going to move. So the dx dt tells you the direction in which x is going to move. So think about begin with x0 and take a small amount of time delta t. Then in that small amount of time delta t, we know what the dx dt is. Dx dt at time 0. That will be f of x0, 0, right? That will be the dx dt at time 0. So we know the direction of that from 0 to delta t. And so what we can do is we can have an x0 plus delta t times that slope, which is dx by dt at time 0. So that gives you the value at x delta t. You see, so we have gone from x0 to x delta t. Now we are bootstrapping. So once we have x delta t, we know what is the value of x at delta t. So we can put, for this xt, the right t here, we can put delta t. Forget the ut right now, and you put for this t delta t. When you put that, we get the slope at delta t, right? When you get a slope at delta t, we can use that slope from delta t to 2 delta t. And when you do that, we can again multiply that slope by delta t, and we get the value at x of 2 delta t. So you can see that beginning with x0, I can get the value at x delta t. Then later on, I can value at x2 of delta t. If you keep going like this, we are getting the values at the delta t intervals. So we get value of x0, then we have x of delta t, then we have x of 2 delta t, then we have x of 3 delta t, and so on. Now if you take delta t to become smaller, so we have a finer mesh of an xt trajectory. Again, let's make that delta t even smaller. So we have even more points on this trajectory. And now let delta t go to 0. When we let delta t go to 0, we are basically solving the differential equation. So what I mean by is that the differential equation allows you to start from an initial condition and move on like a bootstrapping fashion and continue to find the value of x all the way from 0 to whatever time that we want to go to. Okay? Any question here? Now what comes is a control variable ut. So if I give you ut already, which is the control, let's say my decision variable, and suppose I say ut equal to 5 times t, that's what I'm going to control. Then this is basically a differential equation again. So for any given function ut, again I can solve the differential equation, because in order to do dx dt, I will find that value of ut, that value of xt, and value of t. So I get my slope, and I can continue the same way. What happens in control theory that this ut is not given to you. This is the ut that we want to optimize. We want to find an optimal decision. But the optimal decision will be a function of xt and a t. Okay, anytime I know the value of xt, which is my state, and I know the value of time t. So xt and t, I will know xt and tt, and u will be a function of that xt and t. That's we call a feedback control. Then I can again compute the slope, and again I can compute the trajectory. So the idea is to try to find out that optimal control, because once we have the optimal control, we can put that optimal control back in there, and as we go along time, we can continue to find the trajectory, and that would then be the optimal trajectory. Because I'm using the optimal control here, then when I solve the equation, I will have the optimal trajectory of the state variable. Okay, so this is, so I have a ut, which is the control, and I have xt, which is the state. Once I have this trajectory at each time t, I can put that into this thing here, and there's a big F. That is my profit at that time t. So I will integrate that profit from 0 to t. So I get the profit from on the interval from 0 to t. And at capital T, which is the terminal time, I have some state, and I can sell that state, and that state will be my salvage value. So what I want to do is I maximize the profit from 0 to t and the salvage value at capital T. That is my objective function. So what I want to do is to find an optimal control trajectory u of t going from 0 to capital T and maximize this j. That is actually the optimal control problem. And it is possible that that control may be not completely unconstrained. That control may come from some set omega t. For example, a set could be from 2 to 3. So that means the control can take only the value from 2 to 3. So that is an example of a set. So I should only be able to choose that control from that set at each point in time. So a simple optimal control problem has a state equation, which depends on a control, has an objective function, which depends on state and control, some restriction on a control, and our idea is to find this optimal control. What is the decision that we make? Now, this will become more clear as I give you 2 or 3 examples, and then we can again see what is going on.
Excuse me, Professor B.
Yes.
Before you proceed, so ut could be a function of t. Can it also be a function of both xt and t?
It can be a function of t, it can be a function of xt and a t. It could also be a function of only xt. It depends on the problem. But in general, it will be a function of xt and a t.
Okay, I see. So,
Because that's at any point that's given to you.
okay.
So your control should depend on what you know right now, okay?
Okay, I see. Thank you.
Yeah. In a very general setting, when this depends not only just on t, but suppose x dot t depends on the previous values of t.
Mm-hmm.
That means it may depend on the whole past trajectory.
Okay.
That's a more complicated problem. That will give you an integral differential equation, and
Yes.
there are theories available to that. I have some papers on that. There are references, but let's not get there right now.
Okay.
Okay. It is also possible that there are some constraints on x and t and u at any given time t. So we're going to consider these constraints to be mixed inequality constraints, because at any time t, I must satisfy this constraint. Xt and ut must satisfy this constraint. So they call mixed constraints. They may also be constraints that do not involve u. That means does not involve control variable. These are called pure state constraints. And the reason I make a distinction between two is because these are easier to handle. These are more difficult to handle. So these are dealt in chapter 3. These are dealt in chapter 4. So what we do now is we're going to deal with this problem in chapter 2. We're going to deal with this problem in chapter 3. And we're going to deal with this problem in chapter 4. Okay? It's also possible that I'm not allowed to have my terminal state to be anywhere. Maybe I will require terminal state to be between some values or in some set. Okay, so that will become the reachable set. Uh, uh, so um, I think that is not. There should be something else here. Is there something else here that is not? Okay, we'll talk about this more. There may be a slight notion of terminology here. Right now, I'm using xt to be the constraint in this particular set. Okay. So let's go through 3 examples to understand what we mean by state and control and things like this. Okay. So first example is the production inventory problem. So at any given time t, I have the inventory. So IT then is the level of inventory at a time t. And so I have given that inventory. I'm given that inventory at time t, and I want to decide on how much to produce. So PT is the rate of production at time t. So that's my control variable. That's my decision variable. Control variable, decision variable are synonymous. Okay. Now, if I use the rate PT to produce, and if my demand is given by ST, then we know that the rate at which inventory is changing, which is I dot T, is PT minus ST. Okay, so now we got a differential equation which has a control on this side and some function that is given to us called the demand function on the right hand side. Okay, we don't have any I on this side here, but can anybody give me an example of a simple example of what I have to change to this inventory problem to make to bring IT on this side? Anyone? Kai?
Yes. So, Professor, can you repeat your question?
Okay.
Why we should have an
Maybe
I?
let me ask a question to somebody who's in operations management. So,
Sure.
leak it. Suppose. See, right now, remember now, if you go back to my initial thing here, you can see that X dot, which is the I now, right? I is my state, right? Inventory is my state. On this side, I have I, U is my production, P, and T is T. Okay. So I don't have any I on the right hand side, which is okay if you don't have it, that's fine. But my question would be, well, how would I change in a very easy way to have IT on this side to make the problem more complicated? How would you do that? What would it take us to do that?
Sorry, but I haven't found the method. Should we integrate the
No.
right?
Integration doesn't come in.
Oh,
We
so,
are,
so I
we are
don't know
modeling.
now.
We are modeling. Okay, let me give you an example. Suppose my IT, which is the inventory, suppose it spoils. Suppose IT is amount of apples, and they spoil at a certain rate. Okay, then suppose the rate of spoiling is delta. Then you will see I dot will be PT minus ST minus delta times I, right? Because the inventory is being built up by production, it's being depleted by demand, but it's also being depleted by inventory that is getting spoiled. And that would be the delta times I, where delta is the rate at which the inventory is becoming useless, right? So we will have a minus delta IT on this side, and that would be a state equation with the state and the control on the right hand side. So that would be a slightly more complicated example of a production inventory model. Okay. Now let's look at the objective function. The cost of inventory is called cost of holding inventory. It's given by H of IT. Okay. And the cost of production is given by C of PT. When I produce something, it costs me. So this is the cost of inventory. This is the cost of production. But since I want to minimize the cost, I want to maximize the minus of the cost. And the reason I'm doing it is because some book developed the theory on minimization problem, and some book developed the theory on maximization problem. They are equivalent, right? So what I'm going to do is to develop most of the theory on maximization problem. And so if I have a cost minimization problem, I will just put in a minus in there and maximize it. So we don't have to develop the theory for maximization and minimization all the time. We just develop the theory for maximization, and then we can change the objective function to minus of the cost. So that will become a maximization problem. So we don't have to do two different set of recipes. Okay. Okay. That's a state constraint. This is a pure state constraint. IT is bigger than equal to 0. That means I'm not allowing the inventory to be negative. Okay? That means that at some point in time, I may have to increase the production to some level so that my demand will not deplete my inventory and bring me to the negative inventory. For those people who know operations management, that means I don't allow backlogs. So the demand cannot be backlogged. Backlogged inventory is a negative inventory. Okay? The control constraint, which is the constraint of control constraint is a constraint of this kind, for example, is given by here. For example, my production cannot be lower than 0, and my production PT cannot be lower than P min. That could be some number bigger than 0 if it's necessary, and my production cannot be bigger than P max. So I have two bounds on production, which means that I should produce only within those limits because my machines do not allow me to produce more than P max. And my machine may not allow less than 0. But it's also possible that some machines you cannot run lower than P min. What is going on here? Yeah. So basically, these are bounds that are given to us. We can also say that my final inventory cannot be lower than I min. That means I don't want to leave the system with an inventory which is less than I min. So I want to keep the system because maybe the company is not going away. Maybe suppose we solve the 1 year problem. Suppose T is 1 year. So we solve 1 year problem. Doesn't mean that company is not there after 1 year. So you may not want to leave the next year with no inventory in the beginning. So in that case, I may impose a constraint like IT equal to bigger than I min. Okay, so we already know these. We already talked about these. So we are, any question on this one simple problem of optimal control in the inventory problem? Okay, I may have not told you that, Min may have told you that. I give you a homework, 2 problems from the chapter I teach, and 1 problem from the chapter I teach next lecture. Okay, and the idea is that I'm asking you to read the next chapter, which is the chapter for the next class, before you come to the class. I'm going to run that as a PhD level course in which you are supposed to be reading. And when you come to the class, I may go with a higher speed, but you can stop me anytime you want. And you can ask me any question that you do not understand reading by yourself. And so my session will be more like going through the chapter, but going in a way that will be stopped by you anytime you have a question that you didn't understand, or you have a question or new questions that come when I go over the lecture. Okay, so I've been doing that for maybe more than 20 years, and that is the system that I'm going to follow again. And so please make sure that I don't know when. I think we hope to finish this today, chapter 1, but because the chapter 1 is basically notation and statement of the problem and a little bit of history, and so it is really there's no theory being discussed in this chapter. A lot of notation. Okay, So that's our problem in production inventory. Let's look at the next problem. The next problem is problem of marketing. In marketing, there is something called a goodwill. So at any given time, the company has a goodwill, which is GT. Goodwill now is a state variable. It is also could be considered as an asset. Though for those who in accounting, it is, you can carry that as an asset of the firm. So we have a goodwill, and we build the goodwill by advertising. So UT is the rate of advertising. And so the way it is built is like this. G dot T, which means the rate at which the goodwill grows, is UT minus delta GT. That means that it grows up linearly with advertising amount, but it also depreciates. Just like every asset depreciates at a certain rate, goodwill depreciates. And so the goodwill changes. Increases in goodwill comes from advertising, decreases in goodwill comes from depreciation. Once again, we have a differential equation, and we have initial goodwill. There's a value of the goodwill, which is pi of GT. That says that goodwill will give you some sales, and the sales will give you some revenue, and that revenue, and there may be some cost of that sale. So that will be given by a function called pi g. And UT is the cost of advertising. So that gives me the profit at time t. And because I have an infinite horizon problem this time, I'm going to discount that with some discount rate. So the rho is a rate of discount. And in continuous time, when you discount, it's e to the raise minus rho t. Is that clear to everybody? This is generally what we do when we discount in continuous time. If we discount in a discrete time, you divide by 1 plus rho to the power t. Okay? But if you continuous time, it becomes e to the minus rho t. In fact, you can go from discrete time to the continuous time formula by some kind of a limit process. Okay? So you discount by 1 plus rho to the t, but then you take the interval to be smaller and smaller, and so it becomes, and when you take the limit of that kind of thing, it becomes e to the minus rho t. You might want to derive at home to go from a discrete discounting process to continuous discounting process. Okay. We have a possible lower bound and upper bound on advertising rate. And this is a gross profit rate, which means the profit that, when I say gross, it means the cost of production to do that sale is also included in that. Remember, there's no cost of production here. This is just the cost of advertising. So all of the profit is a gross of advertising, not gross of cost. The cost is already part of this. Okay. Any question on marketing problem? We have no rush to finish the whole book. If it's better to learn what we can, and so if you come to the class and have a lot of questions, we will field those questions. And if that slows me down, that slows me down. Okay? It's better to learn a part of the material very well than not learn anything when you go and try to finish everything. I mean, generally speaking, we will finish it, but it's up to you. Okay? How far we go, how fast we go may also depend on, how the class is conducted.
Professor, sorry, I don't have a specific question about the content, but I have this question about the course as a whole. I have this feeling that this is like the system dynamics course, which we use Vensim, application to model these kinds of equations and, state variables and things. Am I right, or I'm getting it in the
Yeah,
wrong way.
the system dynamics usually does not optimize.
Yes,
So
it
if I
just
give you,
models.
if I give you, if I give you, if I give you the function of production rate over time, right?
Yes,
Then you can actually find the trajectory of inventory using system dynamics.
yes, yes. We can
But
see the
right now, so,
changes.
right, yeah, you system dynamics basically tells you if I give you the advertising, you can tell me what the goodwill would be, okay? And you can also
Yes,
integrate this to give me the profit.
yes, yes.
But it does not tell you how to find the optimal profit.
Oh, yeah. We have to, change the different variables to find the optimal level
Okay,
somehow.
so you can do simulation. So here's something what you can do. You can take a one trajectory like this, another
Okay.
trajectory like this, right?
Okay,
And
yeah.
you can find the profit for each of these trajectory, right?
Yes, yes,
But there
right.
are infinitely many possible trajectories.
Yes,
So
yes. That's, yeah.
if I give you a few trajectories, you can find the best of those, right?
Yes, yes.
But I'm interested
And
in finding the optimal among all possible trajectories.
yeah, yeah. And finding
So
the optimal level is much harder in that way. Yeah, I got it. I got it.
yeah,
Thank you.
think of a problem, a static problem. Think of f of x as a function
Yeah,
of x, and I maximize f, right?
right. Yeah.
So how would I do? The first order condition is f prime x equal to 0, right?
Yes, yes.
And then I solve the first order condition, that will give me the maximum of
Yeah.
minimum. And then I solve that f prime x equal to 0. Maybe there's only one value, in which case I got the maximum. Maybe there are 5 values, in which case I got the 5 local maximum. And I want
Yes.
to find out one which is the global maximum.
Yeah,
And if
yeah,
I do the
right.
second order condition, I can tell you whether that's minimum or a maximum, right?
Yes, 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 yes.
I want to now tell you that the optimal control theory will give you a first order condition, which is the
Okay.
generalization of f prime x equal to 0.
Yes. And how about the second order?
The second order
We don't have.
condition, we do not do that. We do sufficiency condition.
Okay.
There are second order conditions, but since we are only maximizing, we only look for maximization. And so
Okay. Yeah.
we don't go into the second order condition because we don't want to look for a local maxima. The sufficiency
Okay.
condition will give you a global maxima. The maximum principle that we give you is also going to be for global maxima. But that doesn't mean it's an easy problem to solve. I'm just telling you there are second order conditions and stuff in the literature, but we're not going to go there.
Okay. Yeah. Thank you, Professor. Thank you.
I'm just giving you a comparative analysis of what is going on.
Thank you.
Okay. The third problem is what is called a consumption problem. I devoted part of my life solving that problem. WT is wealth, and a CT is the rate of consumption. So this is a problem of an agent who wants to maximize his utility of consumption over time. Okay. So if you consume at the rate CT, then W dot T will have a term minus CT because whatever you consume gets subtracted from your wealth, right? But your wealth is deposited in a savings account, and the savings account earns the interest rate of R. Okay. So with the interest rate of R, my W dot, which is the rate at which my wealth is changing, is amount of interest that I gain minus consumption, right? And I have initial wealth of W0. And then every time I consume, I derive a utility of consumption U of C of T. As you can see, UC is the utility of consumption. And I discount that by rho. So that's e to the minus rho t dt. I integrate from 0 to t. When I do that, for any given consumption trajectory, there will be some wealth left at WT. So when I have some wealth left, that value is the bequest, which means that this is the wealth, let's say, goes to your children, and you put some value of what goes to your children. Okay. So you want to maximize your utility of consumption plus your utility of what you give to your children. Together, you maximize. And that one can be discounted by the factor at capital T. And then you have an objective function. And what you want to do is to choose the consumption rate over time, keeping your wealth always bigger than or equal to 0 so you don't become bankrupt, and maximize that and find the optimal consumption path. So it's a third problem that I have, which is an optimal control problem. And notice now, every one of these problems that I gave you has only one state variable and one control variable. But in general, there may be more than one state variable and maybe more than one control variable. For example, in inventory problem, you could have two different goods. So you have inventory 1 and inventory 2. One for apple and one for oranges. There could be two inventories, for example, right? So that will be two state variable. And then the production will also be 2 in this case. In general, we are looking for a state variable which could be n-dimensional in general, and we are looking for a control variable which could be m for Mary dimensional. So that's why I ask you to have some knowledge of vectors and matrices, because we're going to develop the theory which is good for vector state variables and vector control variables. Even though most of the book and most of the problems are generally going to be one state variable and maybe one or two control variables, but generally speaking, those are the ones that we're going to be dealing with. But the theory will be more general. Okay. I want to go through very quickly the history. I want to spend less time on it because we spent a lot of time trying to figure out how the Microsoft team works. Thank you, Kushali, for giving this to this level. Okay, so very quick history. There is a theory called calculus of variations, which is kind of prior to the optimal control theory. It's quite related, and there are courses available on calculus of variations. You can have whole books on calculus of variations. These were developed before the optimal control theory, and they are related. Okay, so I'm just going to leave it at that right now. And one of the most famous problem of calculus of variation is called Brachistochrone problem, or path of least time. We'll quickly look at that. And many of the big guys in physics and mathematics actually contributed to solving that problem. And then in 1958, a bunch of Russians developed what is called the maximum principle. And the maximum principle is like the first order condition of optimality for an optimal control problem. Okay? It is like f prime x equal to 0. Basically, that's what's going on. You are taking the derivative in a high dimensional space. You know, the space is so think about this way. If I give you the whole trajectory, then for any given trajectory of control, then that is the function, which is a function of the whole trajectory of ut, right? That is the variable. The variable is not one variable u, which you can take the derivative with respect to. I have to. So this j is actually a functional. Functional means it's a function of a function. Okay. So here is a functional, and it's a function of another function, which is u of t. So I have a j, which is a function of a trajectory ut. And so if you could take the analogy, I have to take the derivative of j with respect to the trajectory ut. And trajectory ut is infinite dimensional because it's got infinite dimension, right? because there's a value at each t, and the t is continuous. So you see, I'm sort of trying to take the derivative of j with respect to u trajectory ut, and I'm trying to equate that to 0. So that's that. But it's more complicated than that. But in abstract terms, that's what I'm doing. In the abstract terms, I'm actually taking the derivative of j with respect to a function called ut. Okay, so I'm taking a derivative of functional with respect to a function. That's the analogy to the problem of calculus, minima and maximum of calculus.
Excuse me, Professor. I notice you usually use the trajectory. So by saying trajectory, are you trying to say?
Yeah, let's go. Yeah, I understand what your question. So let
Uh-huh.
me give you the question. Let me give you the answer right now. So
Okay.
here's a problem of brachistochrone. Okay,
Uh-huh.
the brachistochrone problem is like this. Suppose I give you a bead. There's a bead sitting here at A,
Uh-huh.
and I give you a wire. Okay, the wire has to go from A to B. Okay,
Okay.
and the bead will slide along the wire to B. Okay,
Uh-huh.
so for example, I can do the wire like this, like this, like
Uh-huh.
I bend the wire like this. That is one trajectory, right?
Yes.
And the bead will slide along that wire.
Okay.
If you give me the shape of the wire, then I can use the gravitational formula to compute the time required to come to here.
Okay.
So the time from A to B is a function of the shape of the wire, right?
Uh-huh.
Now, suppose I give you the wire that goes like this and goes like this. So it goes very fast like this. The bead will slide all the way up to here, then it will just stay there, right?
Mm-hmm.
And then it will not go anywhere because the gravity will not go along here, right?
Mm-hmm.
So the time associated with that wire shape is infinity, right?
Yes.
Okay. Somebody may argue that I can put the wire as a straight line, right?
Uh-huh. Uh-huh.
But the straight line gives me the minimum distance of the wire, right?
Yes.
But when the bead slides along it, I don't know the time it will take. But I can find the time. I don't know if it's maximum or minimum or anything in between.
Uh-huh.
So the idea is to find the shape of the wire so that the time of the bead going from A to B is the minimum time.
Okay.
Okay?
Okay.
So the time is the objective. So that is our functional. Okay? That is our big F. And the wire shape is our U of t, which is the function of so call this U, call this t, then that trajectory can be called as U of t, right?
Mm-hmm.
So t, capital T, which is the time, or F, which is the time, is a function of this trajectory U of t, which is the shape of the wire. And now I have to take the derivative of that function with respect to the shape of the wire.
Uh,
That's what I mean by the trajectory. Okay, suppose there are only 3 points. Suppose the wire goes, suppose I'm allowed to go, suppose I'm only allowed to have 2 bend in the wire, right? So I
okay.
can bend the wire here, I can
Uh-huh.
bend the wire here, and I can
Uh-huh.
bend the wire there. Then the time is a function of only 2 variables, right?
Yes.
Because I can tell you where to bend, right?
Yes.
So
Yes.
that is a coordinate, that's a coordinate. So time is a function of only 2 variables. But because time is continuous, wire can be continuously bent. It's no longer 2, it's infinity, right?
Yes. Yes.
So I have an infinite dimensional trajectory, and my function is a function of an infinite dimensional trajectory. And in order to do the first order calculation, I have to take the derivative of the function with respect to an infinite dimensional variable.
Okay.
So you know how to take the derivative with respect to one variable. You know how to take the derivative with respect to 2 variables. You know how to take the derivative with respect to n variables. Okay?
Uh-huh.
Now let n go to infinity. So I need to find a derivative with respect to something that is infinite dimensional. Okay? So now let's coming back to this problem. Well, it turns out that at the beginning I want it to be very fast, right?
Yes.
Because I want the beat to accelerate very fast. But at some point I have to move, because if I don't move all the way to here, I will not go to this point.
Yes.
So I could go something like this very fast and then go like this. But then it's very slow, right?
Yes.
Because this is very slow. Or I can go not so fast and then have a fast later on, right?
Mm,
Because if the slope is lower here like this, then it'll be very slow. If I go like this, it's faster.
oh, yeah.
So trajectory has to be somewhere between this. This is the upper, this is the lower bound, right?
Mm-hmm.
And we can assume in general this will be the upper bound.
Oh, yes, yes.
But I can tell you that the straight line is the upper bound as well. You can actually find out that the straight line is not an optimal solution. And anything going above the straight line is only going to slow down, right?
Uh-huh.
If my wire is like this, right?
Uh-huh.
Like a concave function, then it will actually slow down.
Yeah,
But
it will keep.
any
Yeah.
concave function can be worse than a straight line, right?
Uh-huh.
So we know the straight line is kind of an upper bound.
Yes, yes.
Now, a lot of people thought straight line is an optimal solution because it takes less distance to travel.
Mm-hmm.
But it's not the case because acceleration is important.
Okay.
So the wire actually is of this shape. This shape is a cycloid. So to find out that this is the shape, it took several years by these guys to solve that problem.
Oh,
Okay,
okay.
I have the literature and the references for you to look at this, and I think in appendix it has been solved for you. So I don't want to go through that right now, but that is a historical problem of calculus of variation.
Sure, sure. I will look into it after our class. Hope I can understand that.
Yeah, at least it gives you the idea what is going on
Yeah,
and
yeah.
what was the calculus of variation people did. Remember, Leibniz and Newton did not have the optimal control theory. They only had calculus of variation.
Oh, okay.
But something developed based on calculus of variation, not that much different, but sufficiently different that we call it a maximum principle. And the optimal control theory can be said to originate with 1958 theory of Pontryagin. It's called also Pontryagins maximum principle.
Okay.
I met Pontryagin on an aeroplane at the airport. At an airport in Vienna, I met this guy because he was going to a conference and I was also going to a conference in Russia. So I met him, and apparently Pontryagin was blind since birth, and
Oh.
his mother gave him German mathematics books because Germany was very high level in math at the time,
Uh-huh.
and he could not read it, so his mother read the book to him, and he learned mathematics like this. And eventually he founded a team of people, and together they developed this theory of maximum principle. So when I gave my book to Pontryagin to sign, he gave it to his wife, and the wife signed L.S. Pontryagin. I did not immediately ask why this is so. And later on, when I reached Moscow, Russia, I asked somebody, I said, why did Pontyagin's wife sign my book? He said that she signs his checks, she signs his books, because he was blind from birth, he doesn't sign anything. His wife basically is the person who signs everything for him.
Wow.
So I have a signed copy of Pontyagin's book, but signed by his wife.
Oh. Nice.
Okay, that's a little history. Okay, so that's a notation. There's equal sign, there's defined to be equal, but this can be used also for many of the things. It is not a hard and fast rule. Sometimes I can use this for this, but just generally speaking, you should know what these mean. Sometimes this means identically equal to. So I don't, if I use this, it actually means this. If I use this, it actually means this. But that can mean any of these, okay? some people don't always use this. They can use this for the same reason. Okay. So that is a more general symbol that we use. These could be used if you are very particular about using them. This is approximately equal to, this means implies, this means for all, this means member of, and this is the end of the proof. If I have a theorem, there's the end of the proof, so I do that. Okay, does anybody need a break or should we just continue today? Nobody needs a break, right?
Yes, Professor, I think we can move on.
Huh?
Yes, Professor.
Okay, so we can at least gain 10 minutes. Good. So, very quickly, this is a column vector and column vector. It can also be written as a transpose of this. So I can write column vector like this. And this is a row vector. Okay? And if I take the derivative of a column vector, it will be a column vector. If I take the derivative of the row vector, it will be a row vector. Okay? So far, so good. If n equal to m, and if row comes before the column, then that is the inner product, and that is one dimensional. Okay? So I have a row and a column. And if I multiply a row and a column, and if they have equal dimension, then that is called an inner product, and that gives you one dimension. So everybody knows that, right? Oh, raise your hands if you don't know it, so we can spend more time on that, okay? That's a matrix, Aij. So it is a matrix with m rows and k columns. No, k columns and m rows. So it's m by k matrix. And it is important to see that I changes this way from top to the bottom. And a j is the second variable. It changes. You see j is 1, j is 2, j is 3, j is k, right? So j goes like this. So j is changing this way, I is changing this way. That is a standard notation in the literature. And the way I remember is, so think this is a tree. Think this is a tree. Tree is always like this. Tree is a column. And the bird is sitting on the top of the tree called blue jay. So J is one J is sitting here, one J is sitting there. So J is sitting on these columns and they change like that. Okay, so this is one way to remind yourself. And then you can see that if A is a m by k matrix, B is a k by n matrix, then this k and this k is common. Then I can multiply this by that. I can multiply, and that's called AB. And AB is multiplied this way. It is a matrix C, where Cij is given by this. So you multiply the ith and the jth column, and then you get this. Okay? So far, so good? If I have a function that goes from one dimension and takes the values in k dimension, then it's called a k-dimensional function of a scalar variable t. T, and it's become df dt. So if I take the derivative of that with respect to t, and since f is k-dimensional function, it will become f1t, f2t, fkt. Okay, just 1 second. Yeah, if it's a column vector, then it's f1t, f2t, fkt. So that's standard. So all this is very simple. Now there is something a little bit more complicated, but again, I'm using a standard notation. If you have an old version of the book, that is completely changed. I'm now using a more standard notation. In the old version, I chose my own notation, which was different than the standard notation. Okay, so if I have a function f of yz, it is a scalar function, but y is n-dimensional and z is m-dimensional. So function f takes this kind of space into E1. Okay. So here's something you have to learn. The derivative of such a function, regardless of what happens to y, what is z, is always a row vector. It is called a gradient. So f sub y and f sub z are called gradient of f with respect to y and a z. And the gradient is always a row vector. Okay, these are all notation. It could be also column if you want, but then you have to develop another way to take derivatives. So this is just a convention. It is not. It's not coming from some deeper version. It's just a convention. So let's just stick to the convention that other people stick to, and all the books and most of the books would adhere to this convention. So f sub y is a row vector, regardless of whether y is a column or a z is a row. It is a column vector. Fz, even though z is a row, is also a row vector. Okay, so fy and fz are both row vectors. Remember that. Now comes the next level. Suppose f is now a function that takes the en and em to k dimension. So it's not the scalar function like this one, like f. It is now a function which is k dimensional. So the f is like f1 k. This is the function. But f could also be, so right now it's a k dimensional function. It's either row or column. I don't really care. Okay, it could be row or column. It doesn't matter, because the derivative with respect to this will follow the same rule. Okay, so f could be row, or it could be column. So you can see what is going on now. Fz, I'm taking the derivative of f with respect to z. So z, y and a z. Z is a row vector, y is a column vector. I'm taking with respect to z. But because I take with respect to z, every function f, every component, the derivative with respect to z is a gradient of that. So here's that gradient. You see it's a row vector. So that is the gradient of f1. That is a gradient of f2. And that is a gradient of fk. Once you put that, you got fg as a matrix. So delta fi, delta zj is the ith, jth element of that. Okay. So when you put ij element and put a square curly bracket, that is the same as the matrix. So you notice why it's Cij. So C is a matrix. It also can be defined this way. So if I put the ith, jth element and put a curly bracket around it, that also is a matrix. Okay, so it's another way of defining the matrix. Okay, so the way I define fz is by defining the ith, jth element. And once you define the ith element, you can write it this way. So for those who doesn't want to, for the books that doesn't want to take so much space, they can just do fz equal to this. And that is automatically understood. From this comes this by definition. Okay, so that's that. And if I do f sub y, it's the same thing. Y, see the gradient of f with respect to y, with respect to y. So fy is again a matrix like that. So if you follow this, then we know that fz is same as f transpose of z. And it is also same as f of z transpose. It's also same as f of transpose of z of transpose, because they are all the same. This, all the same. Same for y. So far, so good. So what we're trying to do is to learn taking the derivative of a function with respect to vectors and do it in a way so that we don't have to rewrite things like matrices. We can just like this and go through the process. Okay. Now what happens? So I have a function f, which is the one-dimensional function that was in this slide. But if I take the derivative of that function with respect to y, then that derivative is a gradient. and that's a row vector. So now I'm going to take the derivative of the gradient, which means I take the double derivative of f. So that's what I'm doing now. So if I take f of yz, which is same as f sub y of z, but f sub y is a gradient. So z of f y z is going to be this matrix. I can follow the same rule of this rule to here. I apply this rule, the previous slide rule, to f sub y, because f sub y is this kind of function. Is this kind of function. So I apply to this and take the derivative with respect to z. I call this fyz. So you have this matrix. Similarly, fzy is this matrix. Okay, it is given like this. So far, so good. This is the, so why am I doing this all? Because I will need this formula in deriving the maximum principle. So this is also your homework. I think this one is your homework. Is it? 1 point, yeah, 1.10 is your homework, which means derive this formula. So let's look at that. So let's quickly see. I'm not going to derive this for you because derivation basically used these slides that I give you. But look at this. G is n component vector, and F is an n component column vector. So G times F is the inner product, right? So this is inner product is just like capital F. It's a single dimensional variable, okay, of now I want to take the derivative of that with respect to x, and x is a vector. This is one dimensional, x is a vector. So what happens is if x was not a vector, then there's a chain rule. The chain rule says g times f of x and f times g of x, right? Anybody? Yes or no? If x was one dimensional, then the chain rule says take g times f of x plus f times g of x. But if it's vector, then I cannot just do f times g of x. I have to do this. And this is same as this. So that is one thing you have to learn. Okay? In some books, they don't do transpose. So you have to understand that there is a transpose in there. Somehow you have to understand that. But I follow transpose here. So this is our formula for this. Okay? And you use this formula now for f sub x, you will get this. And that we will use in chapter 2. Okay? So this is about the notation. Very quickly, we use a norm. So if I have a vector, the norm of that vector is given by this square root of the sum of the squares. And once I have the norm, I can define a neighborhood. The neighborhood of z0 is all the values of z such that the z minus z0 norm is less than epsilon. Why am I doing that? Because I want to take the derivative, and derivative requires a neighborhood. So in a single dimensional, the neighborhood is just z minus z0 absolute value less than epsilon. Right? It is a ball, epsilon this side, right? But in a multidimensional, you need to figure out what the ball is. That's the ball is this neighborhood, and I have to be able to take the derivative by having this kind of neighborhood. So that is all I'm doing. I'm not using, we're not going to use this all the time. We're going to only use this to give you some idea of what is going on. And then it's just it's sitting in the background, basically. We need a function of order small oz, it's called little oz. And that is a function that says that if I have a function z, and if I take the division with respect to the norm, then if I take the limit of this as z goes to 0, then this is equal to 0. So look at, for example, z square. So if this was a z square, then z squared of divided by z, which is the norm, it will go to 0 when z goes to 0, because z squared is a higher order than z. So that's called little order of z, okay? If I have a function and I want a neighborhood of a function, then I have to also define the norm. So if I have a function zt, which is a vector function, then I take the sum of the components, square of those, integrate from 0 to t, sum of these guys, and then take the square root. So take the square root of component j, integrate it, sum for j1 to m, and then take the square root again. That is the norm. So that's another neighborhood that, once again, I'm not using all of these, but I'm just telling you that you need some of these things to take the derivatives. We need left and right hand limits of a function. So this is the limit from below. So if tau goes to t, so tau goes up to t, then that gives you this limit. We call it xt minus. It is same as limit of epsilon going to 0 of a function when function is from capital T minus epsilon. So epsilon is going to 0. It's the same as this. Xt plus is the same limit as epsilon to 0, x to t plus epsilon. Okay, so I can give you an example. Here's my function. I define a function here. This function has a value 1 at 0, then it's open here, then it's open here. It takes value 4 at 1, then it's open here. It takes value 2 at 2, then it's open here. It takes the value open here, and it will tell you at this point, at 3, it takes the value 3. Remember, a function cannot have two values at any point t. So this is a function. This may not be differentiable everywhere, but that is a function. So if you take that function, you can see the limit. X0 is certainly 1. X0 plus is the limit going this way, so it is 2. X1 minus, which is X1 minus, if you take the limit from this way, X1 minus is 3. Even though the value of X1 is 4, the limit X1 minus is 3. X1 plus is going this way from right to left. So it's going this way. So X1 plus is exactly equal to X1, which is equal to 4. X2 minus is 3, as you can see here. And X2 is equal to 2. And X2 plus equal to 1. So here's an example where X2 minus, X2, and X2 plus are all different. One is this, one is this, one is that, okay? So they're all different. And finally, X3 minus is 2, and X3 equal to 3. So you get the idea of what these limits are. You get the idea of what I mean by them, okay? Discrete time, we, instead of have x of t, we're going to put xk, that's time k, uk, lambda k, which is the adjoint variable, and the difference interval will be xk plus 1 minus xk, which is the, remember x dot will become this in discrete time. Okay, and then we will have a right-hand side. So the left-hand side will be this, right-hand side will be the function f. So that's called delta xk. This is same as the dx dt, or the similar to dx dt. And the optimal path will be designated by xk star and uk star. Some function called bang bang. If I give you a function w that changes over time, then whenever that function is lower than 0, this bang function is value b1. Whenever that function is above 0, the bang function gives the value b2. And when it is 0, I don't know. Anything is possible, okay? It's arbitrary. It'll be defined by some other means, but this function does not take the value. It can take any value between b1 and b2, so it's arbitrary. Another function is called set function. The function, if the function is lower than y1, it takes the value y1. If it's in between these two values, it takes the value exactly of the function. And if it's above y2, it takes the value y2. That means function is bounded by y1 and y2. So if w is above y1, it chops off at y1. If function is below y2, it chops off at y2. And I mean, other way around. Y1 is lower than y2 because y1 is lower than y2. So if it's above y2, it chops at y2. If it's below y1, it chops at y1. And in between, it stays at w. So we will see those examples later. but these are and please read that there are some exercises that ask you to do that, so you can just follow that. Sometimes we have to apply an infinite level of control when U is infinity, and we apply that control for a very short time. So when you apply that control for a very short time, then we need a high level of control to get to very short time. So this should be actually U of epsilon. U of epsilon is the control needed for me to go from x1 to x2 in an epsilon amount of time. And now I let epsilon go to 0. When epsilon goes to 0, this goes to 0, that goes to infinity, U epsilon goes to infinity, but the integral takes the finite value. That finite value is called impulse. So the impulse is impulse is given by this. It's the cost of that control, and I need to have the cost in because I need the optimization. So if I apply the impulse at time t, then my objective function will be integral from 0 to t, then the cost of impulse, then the integral from t to capital T, and the final the salvage value. So you can see that one is really a function between these two given by that. Okay. Do you know any convex function and convex sets? Anybody who doesn't know that?
Professor, we already passed the optimization course, I think. So we actually know.
Did you learn that in any of your classes?
Sorry?
Anyone who did not learn them in the class? I'm going to through quickly. I'm just asking to see what speed I go at. Okay. Okay. So D in n-dimensional space is a convex set. If for each pair of y and z, the entire line segment joining these is also in D. Hey, Kushali, is there a blackboard here that we use on this kind of meeting that I can draw something? No. Okay. So you know that a set like that is a convex set, but if I go like this, it's not a convex set. That means if I take any 2 point in the set and I join the line has to be all inside the set. Okay. So that would be a convex set. If I take certain number of points, then I take the convex combination of these points. That means so there exists pi bigger than equal to 0, such that the sum of the pi equal to 1 and pi xi equal to y, then that y is called the convex combination. So basically the convex combination is a combination of these points I. And if I take all of these combinations together, okay, then that is called a convex hull. So if I take 2 points, the convex hull of 2 points is just a line. If I take the 3 points, the convex hull of 3 points is just a triangle. If I take 4 points, okay, but if the 4 points are like this, then it will be a quadrant, a 4-point quadrilateral. Okay, but if I take 1 point here, 1 point there, 1 point there, and 1 point in between, then that particular point will not be in a convex hull because convex hull has to be convex. Okay, so if you draw all the boundary points and then those points that go like this, you make them like this, then it will become a convex set. Okay, you got the idea. Okay, it's difficult for me to draw, but that's the difference between the class and this.
I think if you have a light pen, you can use the 1, 2, 3, 4, 5th item on the right. There's a pen there. I think you can try that. Maybe.
Oh, you know this one?
Yes.
Like this one?
Yes, I guess. I'm not sure, but. Oh no, it's not working.
No. Well, if somebody can figure it out, let us know, so we can do something like that. Yeah. I think you need to do some PDF file or something. You have to bring them in. I think, yeah, you have to do this. Edit text and images. Let me do that. Let me try that. And then I put this one. And then, yeah. So that's a convex set. How can I not do?
Professor, the third item is chosen. You have to choose the fifth item.
Which one? This one?
No, the one above that, the pen.
This one?
Yes, a real pen.
Well, that's what I did. That's what I did.
I'm sorry.
Yeah, it doesn't do that. All I'm saying is that if I have 3 points like this, no, it doesn't give me the point. Okay, that doesn't work. Okay, it doesn't work. Doesn't work. So we need to go back, close. How do I do that? How do I go back to? Oh, I go here. I think I know how to do that.
And click the close button.
Yeah, you may click on close and then choose this. Yeah,
Okay.
okay.
Okay. So we need to figure this out. So the function is concave. If for each point of y, z, and for all p, we have this kind of thing. So the function concave is more like a function that's more like that. So if you join 2 points on the function, the line is below the function. That's what it says. So if I have a function and I take any 2 points on the function, and if the line joining that function is below the function, which is exactly what this mathematics says, then that's a concave function. Okay? And if I change this to strict inequality, it becomes strictly concave function. Okay? If the function is differentiable, then if I take a function and I take a tangent to this, and I approximate the function by the tangent, then I'm over approximating it. So the tangent will overestimate the function, then that's a concave function. Okay, so that's what this means. So here you can see. So here's a concave function. If I join these 2 points, a line below it, then that is the general definition of concave function. But if I take if the function is differentiable and I take a tangent here, then you see I'm going to estimate that function here by the tangent. The tangent is overestimating it. It's above that function. So that means that this estimate, the function is below the estimate. This is the estimate. If I take the second derivative, if the function is twice differentiable, then I just have to do this. So that means that if I take the tangent, then the next tangent is lower slope. The last even lower slope. The slope of the tangent is decreasing as I go further and further. So that basically says that if it's twice differentiable, I can do this. So that's the concave function in 3 different ways. Opposite of concave function is a convex function. And so that minus psi becomes the convex function. And every one of these definitions then applies. Okay, so that's good. There's something called affine function, which is kind of a linear, but not quite. So if affine function is such a function that if I take the value at 0 and subtract that, then psi x minus psi 0 is a linear. So if I take a axis, and linear function goes to the origin, but anything translates the linear function to above and below, then there's an intercept. That intercept becomes psi 0. If I subtract that, the function goes back again, the origin. So the affine function is anything that's parallel to a linear function. So as you can see here, this b. So if I take psi 0 becomes b, and this becomes linear function. So that's that. We also use a notation called homogeneous of degree k. That's used when you have a production function. So if I have a production function psi bx, and if it's a homogeneous degree of k, then if I take the b out, it is equal to b to the k psi x. Most of the time we don't use that. We use only degree 1. So degree 1 means that this will be b times psi x. Okay, that means that if I have a machine and I have 2 machines, then 2 machines together will produce exactly 2 times what the 1 machine produces. So that gives you the homogeneous degree of 1. Okay, that's a general. Most of the production functions that we use are homogeneous of degree 1, although sometimes you can do others. So here's a linear function. The simple example is homogeneous degree of function 1. So we have with that. Let's do a saddle point. The saddle point is a point that is maximum in one direction and minimum in another direction. So you can see that's why it's called a saddle. You can see the saddle sitting on a top of a camel. And so you got a saddle, and psi x hat y hat is a saddle point. It maximizes in direction x and minimizes in direction y. It also can be written this way. Psi x hat y is bigger than or equal to psi x hat y hat. It's bigger than or equal to psi x y hat. You can see here y, here's x hat, here's y, here's x, here's y hat. So both of them are the same way. You can do it this way or that way, it's the same. But the picture tells a better story. Set of vectors are linearly independent, linear dependent if there exists pi not all 0 such that this equal to 0. And if that holds only when this equal to 0, then it's linearly independent. Okay, we use it only at one time or another in the book, but most of your exercises and homework will not use this. Okay, rank of a matrix is the number of maximum number of the linearly independent rows, or equivalently the maximum number of linearly independent columns. So the rank of matrix is called min of Mn. Okay, that finishes the course, chapter 1, and we have actually time. So we can, if there are any questions that I went fast, we can go back to that slide. Otherwise, I will start with a little bit of chapter 2. So I'm waiting to see if there's anyone who wants to me to go a little bit further. Anyone? Okay, Kushali, can you give me chapter 2? Is Kushali not there?
Yes, I'm here. Give me 1 second.
The chapter 1 is pretty boring because it's just notation, 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 notation. So I'm glad it's done, and I hope that you will see when we use it. You can come back to chapter 1 if you want to use it. I see Farza. I mean, you have to report to Ganesh, it seems, right?
I'm sorry, I have what?
I don't know. It says send a quick message report to Ganesh Janakiraman.
I believe that means Professor Ganesh is his supervisor.
I don't know. I don't know. I just sighed.
I mean, like our area coordinator is Professor Vijay Mukherjee, and I believe now Professor Ganesh is the area coordinator of OM department.
Right.
So that's why they say reports to Professor blah blah. Means if you have a problem with the student, you can write a report to his supervisor.
Okay.
In the organizational chart, I am kind of like supervised by Dr. Ganesh. That's why you could see Dr. Ganesh.
Okay, well, report to him.
Give me 1 second. This one's
No problem.
giving me a hard time with uploading.
So in chapter 2, we derive the maximum principle. We actually don't derive the maximum principle as rigorously as in some of the control book, like in Portriagin's book. What I do is I use dynamic programming to derive the optimal control theory maximum principle. And dynamic programming, when I use it, it limits me, and I will tell you when it comes to that as to what
Can
are
you see it now, Professor? Can you see this slide?
I see it.
Okay. This is the one that you could use to. It's not letting, right? There is a pen that you could use to draw. No, this is not the one. There's a pen usually.
But I need a blank sheet if I use the pen, right? Not on the slide.
Right.
I
Yeah,
don't want
like Zoom has whiteboard, and then the other one had whiteboard too. I'm not sure if they allow it in here, but we can figure it out for next time.
Okay, let's figure out next time. We can go back. We can, if you have any problem with chapter 1, just let me know and we'll just go back to those slides. It's not a problem. So let's I think it's better to begin with chapter 2 right now, and we have some time, so we're going to just do that.
Right, and then we also need to announce the homework problems at the end.
Well, you can announce them, okay?
Okay.
Okay. Let me, I'm not able to do the arrow anymore for the second slide. For some reason, the arrow doesn't work. Is it because, what is, arrow doesn't work?
Yeah, I'm gonna, I had to give you control. Okay, should work now.
Okay. And is there something to fit the page? Let me see, to fit the page. So it's bigger, or it
Or
doesn't
you
matter?
can click view to make it like formal.
It doesn't matter. It's okay. I don't need to make it large. Can you see it this way, the way it is? If you can see it this way, I don't need to make it large.
Yeah, I can see it clearly. I mean, right now.
Okay, so then that's good. Okay, so as you can see, we introduced the maximum principle as a necessary condition. Remember now, first order condition was a necessary condition. So this is more like a first order condition. Okay. The general derivation is given by Pontiac and et al. In a series of papers from 1956 to 60. The English translation came in 1958, and that's one that I cited earlier, and that's the one that I got signed copy. We are going to give a simple proof, but not completely rigorous proof using dynamic programming. I will tell you why it is not rigorous when that point comes. Okay. Once again, the emphasis in this course is not on rigor, but rather on solving problems. Then there will be examples. I will also give you a sufficiency condition at the end of this, and there will be a computational method, which which is based on Excel, and I guarantee that you know more Excel than I do. So there will be an exercise that will ask you to solve a control problem using Excel, and that is about as far as I go on computational methods of optimal control. The optimal control theory has a huge level of theory when it comes to computations, but I used to have a little bit of that theory as a chapter in the previous editions of the book. But over the years, I did not keep up with the computational aspect of the theory. And since I did not keep up with it, I was not going to revise the chapter without knowing everything in the field. So I basically took the chapter out. So this book basically does not do computation except the Excel. Simple control problem can be solved by Excel, and you will see done 1 or 2 examples by this. Okay, so that's kind of something that you can see. So we already have this, so we don't have to worry about that. So here's our beginning of the definition of the problem. Okay, so we are given in the initial state, which is x0, which could be inventory, could be whatever. But now here's one thing. I'm going to define the problem in a vector form, but you should kind of always think that everything is scalar, because almost everything that works in scalar works almost the same in vector, except in some places you have to put transposes. Okay, and so it's better not to bother too much with the vectors. Just thinking is best done in a single x and single dimensional u. So even though I will write xt is n variable, ut is m dimensional variable, the function is from x and u and t, which is t. So this is x, this is u, this is t into en. So the function is n dimensional because x is n dimensional. So x dot is n dimensional. So all of that. But you should just kind of think that this is 1 and this is 1. N equal to 1, M equal to 1 is the best way to visualize the problem. So f is assumed to be continuously differentiable. We always assume x to be a column vector and f to be a column vector of functions when we do that. And the path xt from t to 0 to t is called the state trajectory. Ut from 0 to t is called the control trajectory, or just simply a control. An admissible control is a control trajectory ut, t0 to t. For ut belongs to a specified set omega t, which is a subset of em. Okay, so that is in a single variable, it could be just the interval. Okay. Omega t is determined by physical or economic constraints on the value of the control variable. Then there's an objective function, which is a quantitative measure of the performance. We can view that as a profit or something that we want to maximize. So this is your profit, and this is your salvage value, and this is the integral of the profit accumulates over time. This is the salvage value which you get at the capital time t. So that is a j, and you have a function f which is taking these values. S is defined this way, and they're all assumed to be continuously differentiable. Okay. The problem is to find a control u star. So notice now, when I say u star here, I actually mean everything from 0 to capital T. So you have to learn the language, what things mean. So for example, here I said ut is a control trajectory or simply a control. So I don't always want to say control trajectory, control trajectory. So you have to understand what is meant in the context. So admissible control u star would have to be a trajectory, okay? Which maximizes the objective function, okay? It's not instantaneous maximizer, okay? And notice also that it is standard in optimal control to suppress this t. You don't want to put this t all the time because otherwise it becomes very messy. So you will see immediately we are here. XUT, no t here, no t here. And that one I have to put t because it is a specified t. And then x dot, again, I don't put t here. Again, I don't put t here, okay, except this t. And you see ut in omega t. And so there we go. And initial value x. So this is how I define my control problem all the time. So this is where the constraint is. This constraint is only control variable constraint. It doesn't depend on x. It doesn't depend on anything, just on time. U star is called an optimal control. And if I use U star here, which means the U star trajectory, then this becomes a differential equation. The state equation becomes a differential equation for any U star. And then that is called the optimal trajectory. Because once I have a U star, I put U star of t here, and then I take the x dot. I can find the trajectory. I take the integral. So all of this is done. So this is called then I get x star. When you put U star here, then I get x star. X star is the optimal trajectory. And I put x star and U star here, I get optimal profit, which is given by J star. So this is some notation again, okay? Important to know that you will find optimal control problems in different books expressed in different way. So this form is the most general form. This is called the Bolza form, where you have an integral of a cost and you have a salvage value. Okay. Now let's take a different form, but they're all equivalent, even though they look simpler, but they are actually equivalent. Okay, so let's look at that. I'm not going into the theory right now. So I can have a problem when S is 0, no S here. This is called a Lagrange form. Okay. I can have a problem in which this F is 0. All I have is this. This is called a Meyer form. And I have even simpler. I can have F equal to 0, and this could be linear. So I can have F0 and S to be like this, C times X of t. which means C1, C is a row vector, so C is a row vector, and X is a column vector, X1, X2, X, and T. So this C of X of T is the inner product, it's linear, and this problem is called linear Meyer form. I want to show you very quickly that case 1 and case 3a are equivalent. That means I can go from here to there and from there to there. So essentially, I need to go from case 1 to case 3a. So every case 1 problem can be changed into this problem. I can do that. So once I do that, some book may actually only devote the whole theory for this problem. But essentially, they also solve this problem because I can convert this problem into that problem. So we're going to do that next. We're going to convert this problem 2.4 into this form 2.5. I want to tell you that when I convert that problem from this form to this form, I will need an additional variable which I will call xn plus 1. Remember, n is general. So n or n plus 1 does not make that much difference in case of generality. So all I can tell you is that when I convert the n-dimensional problem to this form will become n plus 1 dimensional. But then n plus 1 is also general, and so it is not a difference problem. So that's just want to warn you there. So we define a new state vector, y1, y2, yn plus 1, where the first n components are the same as xi. So yi is xi up to n, and then I have a new additional variable yn plus 1. Okay, so that got it. Now I define yn plus 1 dot, because I have a new variable, so I have to define its equation. In order for me to define this form, I need the equation for every state variable. Now state variable has yn plus 1 also, so I define the equation. So I define the equation this way. Y dot n plus 1 is f plus delta s delta x times f plus delta s times delta t. And the initial value of this is x00. S is defined, S is defined, F is defined, S is defined, so everything is defined. So I now define this variable n plus 1, yn plus 1. Okay. Now I write fxyut as f of yut by denoting the right hand side of 2.6, which is this one. I add that as fn plus yut. So because I have a n plus 1 dimension, I have to also change that function f to n plus 1 dimension. So I have to define fn plus 1. So that's all been defined. So now my y dot is x dot and y dot n plus 1, which on the right hand side is f and fn plus 1, and y0 is x0 and xx0. So I have now defined the state variable of which is 2.7. So I have now this 2.5, this equation here has now been defined also. So now I'm telling you that I can, given this, I will now change the objective function. So let's change the objective function. Now we integrate 0 to t, this integral. We integrate this equation. This equation will be then yn plus t minus y plus 0 will be integral of this. And you see that this integral, I'm sorry. This is a full derivative, so it will eventually become that integral. Try to do that at home. It'll be easy to do because you can write this as d of f, and so you can do all of that. So then we have this one. Now I write j to be this integral, which is nothing but yn plus 1, which is equal to cyt, where c is now 0, 0, 0, 0, and the last component is 1. So this is only n plus 1 dimension, but only the last component shows up. So I have now converted the Boltzmann form into linear Meyer form, where the linear Meyer form has a state equation like this, which is n plus 1 dimensional, and the objective function like this, which is very similar. In fact, even simpler than this. because many of the components are 0. Only the last component is Cn plus 1. So you can see it's a linear function of the state. So that's done. So a lot of times you will have the linear Meyer form, and you can see that it is not anything less general. So we're not going to go much further than that. We're going to just define the principle of optimality. Do you know dynamic programming? Anyone who does not know dynamic programming, or at least have one lecture on dynamic programming anywhere? Can somebody tell me?
Professor, I just had some like really principal definition of dynamic programming when I had the operational research course when I was in bachelor.
Yeah, I just want to know that you know Bellman's optimality principle.
Yeah, I do have kind of like.
Okay, then we are going to go through this, and this is my lecture on dynamic programming. It will be very simple, and then we will use this idea to derive the maximum principle next session. So the principle of optimality, it is good for me to go through this very quickly, and then we will leave you. It said that an optimal policy has the property that whatever the initial state and initial decision are, the remaining decision must constitute an optimal policy with regard to the outcome resulting from the initial decision. And we'll use this principle of optimality to derive condition on the value function Vxt. So this is basically what is going on. I'll tell you what the value function is. I'll tell you what it means. So let's go through. Let's think of this to be time 0, and let's think this to be time t. Okay? And this to be any intermediate time. Okay? So suppose I have some kind of a control. So here's an optimal control. So suppose this is the optimal control. And given the optimal control, I can solve the problem up to this time, and I will get the trajectory xt. I will find the value xt here. With this xt, what the principle of optimality says, that this remaining policy is optimal for a new problem that begins here and ends here. Because every time t, I have a new problem from that point to t, right? I can resolve the new problem, right? So if I solve the problem from zero to capital T, and then I come back to some time, so let's say I use the control up to t, and at t, I decide to resolve the problem. Now, if I resolve the problem and I find a different control than what I found earlier, then it's not consistent, right? But Bellman said that the remaining trajectory is optimal. So I'm going to give you the proof and leave you with that. And then after the proof, there are exercises for you. This exercise, which is an exercise using dynamic programming to solve the problem, so you get the idea of what the dynamic programming does in a simple setting, and then we will use this to derive the maximum principle. So here is the proof. If AB is shown in blue is optimal path from A to E, then B in blue is an optimal path from B to E. That's what the principle says. Proof. Suppose it is not. If it's not, then there's another path which is optimal from B to E. Then JBCE, which is the objective value of this new trajectory, this blue and this red, and GBE, which is this trajectory, then JBCE is bigger than JBE, because JBC is better than JBE, because that's more optimal now, right? It's better than JBE. Okay, now, but then ABE is JAB plus JBE. This is less than JAB plus JBCE, which is the JABCE. So I'm now saying that the JABCE is better than JABE. And that's a contradiction because I'm told that this is an optimal path. So that is a contradiction. And the contradiction proves that this trajectory BE is also optimal from B to E. That is that is the dynamic programming's Bellman's optimality proof. It's the simplest proof that I know. You may not find that in some books. But one thing I want to tell you is that this is an important argument here, that there exists a path from B to E which is optimal. So we assume that there exists an optimal solution. And we'll talk more about that later, but we will give some condition for existence of optimal solution, but we will just give them to you. We will not prove the existence of existence proof at all. That's beyond the scope of the course. So I just want to give you an idea that existence is important mathematically, but it is important only for mathematics people. And they've done it for us, and we're just going to use their theory. And that's the end of that part. Okay, so I'm going to leave you there. Please read the book, read the example. The example is not in the book. Sorry. This example, what's going on here? Yeah. This example is not on the book. So you read this example from the slides, okay? And I will go through that example, and once I go through the example, I'll tell you that I use the maximum principle right here. See, I have a 0, then there's a trajectory, then I have a t, there's a vxt, and there's a vxt, there's this one, and I'm going to use dynamic programming here, okay? And that's where that idea will come in the proof, okay? So, thank you. Sorry about running over, and sorry about the initial mix-up. Kushali, we'll try to find out what to do about some kind of a whiteboard, okay?
Okay, and before everybody leaves, I want to assign the homework problems for today. So I'll also be sending out an email, but if you want to write it down, it's 1.5, 1.10, and 2.20. Again, it's 1.5, 1.10, and 2.20. And if you have, like I said, Min is not gonna like spoon feed, but if you're stuck or need help or more guidance, Min is available on Tuesday for tutoring session from 3 to 4. He will be sending out a Microsoft Teams link for that one, and you will be submitting your homework on Teams. You can either handwrite it and scan it and send it, or type it up and send it as a PDF, or handwrite and take a picture and send in the picture. Whatever is convenient for you. But you'll be submitting it on Teams to Min. And it's due by 12:45 on Thursday. So after 12:45, it's late. So you have time from now until 12:45 p.m. next Thursday, which is January 28th.
Okay, I want to emphasize one more thing here. Homework is done so that you kind of stay the course, and I also want you to read that next week's chapter before, because you're going to solve that problem. I'm trying to ask you to read the chapter in order to solve the problem. So that's my way of asking you to do that. But homework only carries 20% of the grade, and generally speaking, most of the people get nearly 20 out of 20. So homework is there for you to learn. It is not there for you to get the grade, but if you don't do it, you're going to lose out. So homework does not improve your grade, but not doing it will certainly make you suffer.